So today we'll be looking at block diagram representation. In the last class we solved we looked at transfer function models. And so if I'm not mistaken, we finished transfer function models. We solved some examples, how you will look at poles and zeros, how you will look at the order of the system, and some other things. Draw the pole and zero map, talk about the stability of a system given the transfer function. So sometimes a system is a combination of a number of systems. Think about any system. Your car, for example, has so many systems in it. You have the braking system, you have the steering system, you have a lot of systems that come together to make one system. So sometimes these systems are connected one after the other in series. Sometimes they are connected across each other in parallel, or a combination of all these things to give you your system. So block diagram representation allows us to look at how we can simplify a complex interconnection of systems to get something simple, something we can work with, to get a single block with input and output, and then we can get a transfer function and do the stability analysis, pole zero analysis, and all those things. So block diagram is a kind of graphical representation of physical system, representing the kind of functional relationship. It is a pictorial representation. Let's, for example, we've been drawing something like this. Where you will see a system, input, output. This is the block. So this is the block diagram for this. G, we have input U, and then we have output Y. So block diagram representation allows us to do this shorthand. So this is how we represent it usually. You have the input, the system, and the output. And remember, we know that the transfer function, well, we'll talk about that. So these arrows, notice the arrows, they represent the direction of information flow from the input to the output. Okay, so usually there are some interconnections, and the interconnections may have different meanings. So if you see, for example, something like this, you see this is going in with a plus. This is also going in with a plus. That means what's going out is x plus y. Let me just make this bigger. Again, here you see the second one, we have x going in with a plus and y going in with a minus. So the signal going out is x minus y. Here we have three signals going in, x, y, and z, all with a plus. Then the output is going to be x plus y plus z. This can also be represented as shown here. So this is how we represent the flow of signals. Okay, so usually a block diagram will have some signals, system block drawn like this, summing junction, which you've just seen like this, where you have input and output, and what we call the take-off points. We will see them practically. So these signals are represented by lines with the name of the signal. So signal RS, signal CS flowing that way, right? So look at it now. We have the system or transfer function is G of S. The input is R of S, and the output is C of S. We've already seen how the summing junction looks like. So this is the summing junction here. So the signal here, C of S, is the summation of R1 of S plus R2 of S minus R3 of S. Then the pickoff point is when you tap from a signal at a point. Now, if you've done circuit theory, all of you, so in circuit theory, remember, we will be saying this signal R is equal to this plus this plus this. So notice the difference. Here in block diagram, it is just tapping the same signal. So this is R of S going to somewhere else. You are still taking the signal to somewhere else, taking it to somewhere else. So it is just a pickoff point. It is not the summation of the signal. Wherever you have summations, you will have this cycle with the sign showing you whether it is addition or subtraction. Okay, yeah, this is just talking about this takeoff point again. Okay, so let's see. So let's see this example. Sorry. Now, if you look, x3 is going out, x1 is going in, a2, x2 is going in here, and 5 is going in. But look at the signs. So we can just say x3 is a1, x1 plus a2, x2 minus 5. Right? But now, this a1, x1 can come from something like this. Usually, the output is, let's say the output here is y. Y is going to be a product of the transfer function of the block A1 times what is going in, x1. So that is why we have A1, x1 at the output here. Right? So, so look at it now. X1 going in, A1 here, we have A1 times x1. X2 going to A2, so at the output here is going to be A2 times x2. And then 5 goes in here. But we know that, again, this is still the same thing. X3 is the summation of these three signals. So if we have n signals, each one with an input x1 to xn minus 1, then xn is going to be the summation of all these products of signals and their transfer, the block transfer functions. Okay, so we'll look at some common ways of interconnecting these systems by looking at the topologies and see how we can simplify complex systems to get a very simple or single block. So let's start. So cascade. The first thing we are going to be looking at is what we call cascade. When we say systems are in cascade, that means they are connected in series. So this is, oops, don't mind my drawing, it's not very good. So this is the interconnection of systems. Let's assume this is G1, G2, G3, and G4. So this is the interconnection of blocks. So what we know that this can be represented by one block G, where G is equal to the product of G1 times G2 times G3 times G4. So it is just saying for a cascade of systems, G is the product of all the cascaded systems. Right? So let's look at an example. Yeah, for example now, if we have this signal E going into G1 and then M going into C. This is the same as just combining here, multiplying G1 by G2 to form one block, and then E goes in, C goes out. So you just multiply the transfer functions, and note that the multiplication is commutative, meaning Gi times Gj is the same thing as Gj times Gi. It doesn't matter which one comes first in the multiplication. So it follows. Yes, if you have systems in series, just multiply the transfer functions to get the equivalent transfer function.
Doctor, what about M?
Huh?
What about M?
Let me go back and see M. Well, when we do that, M disappears because M is supposed to be equal to G1 times E, right? If M is G1 times E, then we know that C is G2. Sorry. Yeah, so in that system, once we connect them in this cascade, M is gone. We don't have that signal M again. Because, as I said, M is supposed to be G1 times E. And C is supposed to be G2 times M. But M is what? G1 times E. So this is G2, G1, E. And if you look directly from here too, C is G1, G2, E. From here directly. So M is once you combine them, then use J is just subscript. Just like I'm saying G1 and G2. So I can be 1, J can be 2. It is just showing you that here, it is trying to tell you that G1, okay, you get it. Okay, that's good. It's trying to tell you that G1 times G2 is the same as G2 times G1. We know that with multiplication, we can move the signals around. Yes, so look at it now. We have R going into G1. So this signal here is X2. X2 is G1 times R. We know that. Then that is going into G2. Right? So X1 here is G2, G1 times R. And then it goes into G3, which will now have G3, G2, G1 times R. Or we can just have our R here, our C here. We know that. We just need to multiply them to get the equivalent transfer function. So this is easy. The equivalent transfer function for Castellier system, just multiply them together. Okay. Yes, Abdul Hadi. Abdul Hadi, you want to ask something? Okay, so maybe you raised your hand by mistake, maybe. So now, what if we have these systems in parallel? For example, here you see we have R. It goes into G1 and goes into G2 so that we'll get C of S. So this is, by looking at it, we already know what will happen because we have, yes, Abdul Hadi, what do you want? Okay, so you see we have the plus sign here, the plus sign here. So we know C, so this is just going to be, if we combine them into one block, it will just be G1 plus G2. Right? Like this now, we have G1, G2, G3. At the output of each, it will be R, because R comes in here, R goes in here, R goes here. So it will be R times G3 here, R times G2, R times G1. And then at the output here, it will just be the summation of those signals. So Look at it, we are saying plus or minus, so 2 will be plus or minus, depending on what it is. So just the others, can you hear me? Can everybody hear me? Cannot speak. You need to, if you want to speak, you have to unmute your microphone. So at the moment you are on mute. When you want to speak, you have to unmute it. Okay. Okay, no worries. If you can't still speak, just type. If you need to type something, just type, and then we can see. Okay. So where was I? Yeah. So we just add them. So now then there is what we call feedback. Now look at this arrow, right? It goes in this way, and then I know we've talked about feedback in the introduction. It goes back through this feedback, and then there is a minus there. So this system has a feedback, right? It is fed back here, and because of this minus sign, we say this is a negative feedback. Most of our transfer functions or our feedback systems are negative feedback. We'll be seeing that. Let's see how we can write the transfer function for this feedback now. So let's do it this way. Maybe I should do it here. Maybe it will be easier. So let's see. So this signal C, we are taking the same signal here, right? So we have C going in here. That means at this point we will have G2 times C. And then here now we have R going in here. That means at this point we'll have R minus G2 times C. So what do we have here? At this point, C so let me just continue from there. So here, okay. So it's better we introduce another signal here, E. So this C is G times E. G times E. Meanwhile, E here is equal to R minus H times C. Because as I said earlier, we have C coming in here. So this place is going to be H times C. And so E here is going to be R minus HC. And then we know that C is G times E. So C is G times E, E is this. So let's substitute for E in this equation. So we substitute E here into this equation. That means C is G times R minus H. And then we can expand it and collect like terms. So C, this is G times R, this is GHC, which we can move to that side. C is common to them into 1 plus GH is equal to C of R. What we want to write, remember, is the transfer function. Remember from the definition, transfer function is the ratio of the Laplace transform output C of S over the input, R of S. Right? For this system, this is our input, this is our output. So from here, we can write the transfer function as G of H over 1 plus G of H. So if you have a feedback system in this manner, with the transfer function forward, we call this the forward transfer function. We call this the feedback transfer function. We call transfer function G and the feedback transfer function H, with input R and output C. Then the transfer function is going to be G over 1 plus G of H. So it is G over 1 plus G times H. Whenever you see feedback, now notice the feedback here is minus. This is negative feedback. This is negative feedback. But this is plus. If this changes to positive feedback, then here will become minus. Okay? So don't worry, maybe this looks a bit complex, but it's not complex actually. Right? So if you have something like this again, it's still easy to simplify. Why? Because this can be changed with G2 times G3. Right? We assume this is, cascade. So G here is equal to G2 times G3. And here again we have another cascade. H is H1 times H2. So you see it has become simple feedback again. It has become simple feedback. And then we can write it as, okay, here again, the signal coming in here can be R times G1 instead of just R at this point. So now once it is in this point, we know, in this form, sorry, we know that this is G over 1 plus or minus GH, depending on what is here. If it is plus, if it is minus, it is plus here. If it is plus, then it is minus. So the equivalent transfer function is G over 1 plus G. There is a special situation where the feedback here, if you see something like this, that means the feedback here, H, is 1. So it is called unity feedback system. So any type of system you have, you can write it as a unity feedback system. And how do we do that? We make this, we try to see if we can make this, we try to make this H1. Transformation 5. Okay, don't worry about this. We'll talk about this later because we've not seen how we can reduce these things. So later on, we will see how this is possible. Okay, so we've seen that cascade can be reduced this way. Parallel combination can be reduced this way, right? So we know these two reduction techniques. Now, let's see this one now. Now, think about this. If you have a signal going in at this point, and then another signal going in at this point. If we want to move this junction to the front of this block, to after this block, what do we do? Now, remember, let me show you. Remember, the signal that is going to come in here, the output at this point will be G times, let's say it will be G times, let's say E. Let's assume this is signal E. Now, if you move the joint to the front of G, that means if we want to have E to still be G times E, we have to multiply by E first. Sorry, G here at this point, and then G down here. I don't know if this is very clear. It's a bit because we are taking this to the point here after G. Okay. Let me see how best to do it now. Yeah. So we want to move this guy to this point after G, right? That means it is here before it has to pass through G. But now that we've moved it here, it has not passed through G. So the only way we can do is to make G here and G here. Okay, it's in my head. I don't know how best to explain it. Let me see. Let's see. Let's assume Y is coming here, X is coming here. So this place will be X minus Y. And this here will have 2 into X minus Y. Now let's assume we want to move this point to this point. And we want to move this block away from there. What do we do such that we have the same thing? So if we do this, remember we said this is 2. And we have 2. Or let me come back here again. Here it is the same thing as 2 times X minus 2 times Y. So instead of doing that, we can change it such that it becomes here becomes 2x, and here becomes 2y. And at this point, we have 2x minus 2y. So you see, we're still getting the same thing. So we're just trying to move this block to come before the summation in such a way that the signal that is after it still remains the same. So I don't know if this makes sense, because at this point it will be, if we have U, input U, output Y, this is G into U minus Y. Here we'll have GU, here we'll have GY, and this place is still G into U minus Y. So whenever you need to move a summing joint behind a block, you have to multiply each of the signals going into the summing joint by the transfer function of the block. That is what this is saying in summary. Get it now? Okay, good. So we have a number of these reduction techniques, and we'll look at them one by one. Some of them, naturally, when you see them and think about them, you will understand them. Some of them may take time and things like that. Now, we want to move this summing joint ahead of the block G. So look at this signal very well. This signal is going into this joint, and then it will go into G. So we'll have 1 over g times g is going to be, at the end, we'll just have 1. So that means if we move this signal to this point, or I'm doing the opposite, that means if we, this signal here going in here, sorry, the signal going in here, we want to move it that it goes in before this joint. Now look at it. If it goes in before the joint, that means it has to pass through G, and it will be multiplied by G. To take care of that, we have to divide it by G, so that if you multiply by the G, they will cancel out. Is it okay? Okay, good. Now again, see now, if we are taking off a point from before it enters G, we can move this point to after G. But because when it goes into G, it is multiplied by G, we need to divide by G to cancel that multiplication. So you see, it's if you look at it, it's sometimes it's not too clear to follow, but once you get the story, it's easy. The same thing with this point now. We have this is going off after G, so whatever signal is here is multiplied by G already. If we take it to this point where it goes in before entering the G, then we have to multiply by G to take care of that. Right? It's just like I have this signal. Let me say this is 4, and I have X here. I know that this X here is going to be, let's say this is Y. It's going to be 4 times Y. Now, if I want to move the X to this point, I have to divide it by, I have to first multiply it by 4, so that I'll just have 4Y. So that's what we are doing. We are just multiplying by that first, since we are taking it before it goes into that. Okay, we've already seen this feedback. We've seen how to get this. And if H is 1, so for unity feedback, H becomes 1 here. So it's just G over 1 plus G. Now, if you have two summing points with 1 minus A going in, 1 is minus B going in, we can just swap them. It doesn't matter which one comes before the other, as long as there is nothing in between them. Or we can even combine them as one point, one signal going here, B minus B in up, and minus A going in from the bottom. But well, this is the point we're trying to look at here. Right. So these are some, this is just summarizing most of those things we've looked at. Again, if you look at it, is the same thing. Right. This is cascade. This is parallel. This is feedback. This is feedback. Again, this is for the summing joints. These are all the things we've looked at. When you move it before the joint, when you move it after, what does it? How does it look like? So let's see. Can we still do something? Okay, let's see. Let's look at this one example. So when you have a complicated block and you need to reduce it, it's just telling you some steps here. You don't need to follow these steps exactly as they are. It may guide you. See, combine all cascade, combine all parallel, edit any loops that you have. So if you have any feedback, remove it. If you have any shift summing points, move them around, and then you keep doing this until you get something simple. Let's look at this now. So if you see this the first time, it looks a bit as if it is complex. right? So let's see how we can look at it. Now we see this is cascade. So we can write this as G1 times G4. So cascade. Now this is parallel combination of two blocks. So we can write this as G2 plus G3. So that means we just have one block here and one block representing this here. Okay, so just as we said, so I said this is, let's assume we have one block here, G1 times G4. Now you see this is again, this is a feedback, right? That is a feedback. So it will be G1 G4 over 1 plus H G1 G4. Sorry, this is, so it is over 1 minus H1 G1 G4. Once we do that, then we have this block here in series with this block here with this feedback. So, and we can combine these two blocks in series by multiplying them, and then we can also take the feedback. So it is a kind of iterative process. So, right, so this is it. We can replace it with this, and then we'll have this now, this in series with this with feedback. Again, this is just multiplying the two of them because it is cascade, and we have this. We can take this, let's assume this is GP or something. Then the transfer function of this is going to be that GP over 1 plus H2 H2 times GP. And you can substitute for this value of GP as that value there. So you see, it's straight if you understand what the steps are. Let's see another. Okay, so what do you think we can do here? So from the way this is, we have to do some, because if you notice this is not cascade. This is not cascade directly because there is a point here that is taking some signals from here. So you have to do some manipulations here. One way we can do it is, can we move this point here? Now, if you move the point there, you see it's supposed to, it is going into G1, which it did not go to before. So we have to divide by G1. So look at it here. We divide it by G1. And then G1 goes, because once we do that, this point can go away. Because we moved it there. That means we have G1 parallel with G2, sorry, cascade with G2, and then feedback. So you see we can simplify this as G1 times G2 over 1 plus G1 times G2H, right? So that is G1 G2 over 1 plus G1 G2 H1. Yes, so that can replace this whole thing. Now once you replace that, you see that becomes one block in series with G3. So the transfer function of that will just be this, what we have here, times G3. Let's follow the block diagram. Right? So this is what I'm saying. We'll have this in G3 with another feedback. Notice it is also feedback. right? So this can be written as this times this over 1 minus this times all of them. Now let me show you. Yes, we can use this systematic way to simplify any. Some are, yes, some are really difficult, but with practice, it is, you can do it with practice. Some are complex, but with practice you can easily do it. Well, I wanted to mention something. Okay, maybe some, if I remember, what was it I was trying to say? Okay, like this, like in this example, remember we'll have what? We'll have G3 into G1, G2 over 1 minus G1, G2, H1 over 1 plus this whole thing in G2, G1, G3 over 1 minus G1, G2, H1 times H2 over G1. Now I want to show you a technique. Notice this 1 over G1, this thing here is exactly the same as this thing here. So mostly what we do is we just multiply the top here by the same thing, this. So this will cancel this, and do the same thing for the bottom here. Sorry, we don't have a space. When we do it, when we multiply this whole bottom with this, then the bottom becomes just this one. Let me use a simple example. This is 2. Let's assume I have x over 1 plus g over 1 minus x over 1 minus g. So you can write this directly without doing this by just saying, okay, let me multiply here by 1 minus g, and let me multiply the bottom 2 by 1 minus g. Notice 1 minus g is the denominator here and it's common here, so that this just cancels that. Sorry for the writing. And then here at the bottom we'll just have 1 minus g minus x. So always this denominator 1 minus g, you can just write it here instead of 1, and then you don't need to write it here and you don't need to write it here. You just write only the numerator of this. I don't know if this makes sense. If it has confused you, it's just a way of simplifying things. If it has confused you, just ignore it. So we have to stop. We have to stop somewhere here, and then we can continue next time. First major exam. You didn't look at the syllables. It is there. Let's see. It is in week 6, I think. But I think we need to have a quiz soon. Let me look at the. I didn't look at the schedule. I can look at it now, and then we agree. The time we have a quiz. and homeworks.
Doctor,
Yes, I'm listening.
for the first major.
Yeah, it is going to be on the 6th of October. Sorry, on the 12th of October. Week
But
6.
how many chapters?
It depends on, let me see. Are you afraid of the chapters?
Yeah, doctor, this is 54 block diagram.
Huh? 54 pages? It's because
Yes.
we are explaining so many things in each page, but I think it is not a big problem. Right?
Yeah. Okay.
Said okay. So, in fact, we are supposed to have, this is week 2, right? Next week we are supposed to have lab. Sorry, not lab. Next week we are supposed to have quiz.
For which
So get
chapter?
ready.
Laplace, doctor.
From chapter 1, from Laplace to,
Just Laplace, doctor.
okay,
Teacher,
Laplace,
Laplace is enough.
you're supposed to do something with block diagram. Okay, let's see. For now, let's leave it Laplace.
Doctor,
Yes.
enough study example.
Yes, you can leave, Ali. Yes, who was talking?
Me, doctor.
Yeah,
Teacher.
if you have class, anybody that has class, you can leave. If you want to talk, you can stay.
Teacher.
Yes.